Remember when we started the chapter on tensors and we said tensors are mathematical objects that are invariant under transformations? But of course, everything we had seen up until now, or at least everything I had seen up until now, till someone talked about tensors, everything was invariant, so it didn't make a lot of sense. So now we're going to talk about pseudovectors, and we're going to see examples of these pseudovectors, and these are objects that are not necessarily invariant under transformations. In particular, the transformations we're going to look at are reflections. And the first example of a pseudovector that is an object that is not invariant under reflections will be the cross product. In this video, we are going to start our study of pseudo objects and in particular of pseudovectors. So this is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail. We will start by talking about pseudovectors in general. So if we consider transformations that involve rigid rotations or translations, movements, there's no way to change a right-handed system into a left-handed system or vice versa without a reflection. And transformations that involve reflections often produce what we call pseudo objects. So this is what we're looking at. We're looking at transformations with reflections. Pseudo objects are very similar to their regular counterpoints parts, except for their behavior when reflected. So we'll look at pseudovectors first, and the first example we'll have will be the cross product, and this is, again will be our first example of a pseudovector. So we'll look at the cross product of two vectors, a and b, where a is a scalar multiple of our first basis vector and b is a scalar multiple of our second basis vector. And when we take the cross product, we're going to get a scalar multiple, a naught times b naught, times our third basis vector, e3. And we see this is, again, a right-handed system. It's been designed to be this way. So if I look at this graph, I have my basis vector 1, my basis vector 2, they're in the same plane. So when I take my right hand and I curve my fingers from 1 to 2, you see our thumb will point in the direction of the third basis vector. Now, because we want to look at pseudo objects, we're going to look at a reflection. And so or another way of looking at a reflection, or an equivalent way of looking at that, is to look at a left-handed system. So the left-handed system results from a simple inversion of the one axis. So this axis here, now instead of going to the right as the positive direction, we're going to have it going to the left as the positive direction. And again, this system can be looked at or as a reflection of this right-handed system. It's just a reflection across the z-axis here. So the equations relating the primed, that's the left-handed system, and the unprimed, that's the right-handed system, are these, that x1 will equal to negative, or x1 prime, sorry, will be equal to negative x1, x2 prime is equal to x2, and x3 prime is equal to x3. So the only thing that changes again is x1 now is negative what it used to be. And the transformation matrix from the primed system to the unprimed system is given here, taken directly from this over here, the equations relating the prime and unprimed system. So now, if we take our original A vector over here that we had in the right-handed system, when we multiply it, we transform it with this matrix, and we'll get that our original A matrix is now negative A naught, 0, 0. We transform our original B from our right-handed system, and we get the same B vector. When we take the cross product now, we'll get negative A naught, B naught, E3, which is exactly the negative of our cross product in the right-hand system. So you see these don't match. So while the vectors A and B point in the same direction, their cross products does not, which is sort of a problem. And so we refer to the cross product as a pseudovector because A cross B is not invariant under the reflection transformation. To get around this problem of having our cross product pointing in the different directions, we'll say a quantity formed by the cross product of two regular vectors is called a pseudovector, while regular vectors are called polar vectors. If V is a regular vector, then it transforms according to our normal transformation matrix A here. However, if V is a pseudovector, we need to multiply our transformation matrix. After we've done our transformation matrix, we need to multiply by the determinant of A. And that's it for our overview. So now we're ready to come back up and look again at our transformations. First, we have a brief introduction to pseudo objects. So if we consider all transformations that involve rigid rotations or translations, there's no way to change a right-handed system to a left-handed system or vice versa. Here I have an x, y, and z coordinate system just rotated, so I rotated the x, y plane. The z stays the same, but you can see the rotations, they're not going to change the right-handedness of the system. Here I have a translation. What did I do? I moved the y coordinate over in the negative direction and the z coordinate over in the positive direction. So this translation also doesn't change the right-handedness. The only way you're going to get a change from a right-handed system to a left-handed system is through a reflection. The drawing we have in our book kind of changes these basis vectors. So one, like the x vector goes out this way, the y direction is this way, and the z is over here. So our reflection now is if we only need to reverse one axis. So we're going to reverse the one axis to 1 prime is going to go the opposite direction. Our x2 prime will, our 2 prime direction will go the same direction as 2, and our 3 prime direction will go the same as 3. And so you can see that this here, if now we go from curve our fingers of the left hand from 1 to 2, we're going to get this up arrow direction for 3. This won't work if we go from 1 to 2 in the right hand direction, right? It would have to go 1 to 2 in the right hand, you'd be pointing downwards. So this here is a reflection across the x2, x3 plane. So think of this as like the plane here kind of separates out the reflection. And I drew my plane for the x2, x3 here, right? So I kind of tried to make it parallel, the top parallel. This is parallel. And so you kind of see that this is coming kind of outward and this is kind of going inward in the opposite direction. I guess you have to use your imagination a little bit. Anyway, to get back to our definition, so to change from a right-handed system to a left-handed system, or vice versa, from left hand to right, you need to have a reflection. And transformations that involve reflections often produce what we call a pseudo-object. And pseudo-objects are very similar to regular counterparts, except for their behavior when reflected. And so we're going to look at an example to see a transformation that involves a reflection will give us a pseudo-object. And our first example is going to be a pseudo-vector, and we're going to use the cross product in order to produce an example of a pseudo-vector. So we're going to consider two vectors and their cross product in a right-handed system. So our right-handed system, going back to the drawing, like your book likes for this chapter, to have the 1 axis this way, the 2 axis this way, the 3 axis this way. So here you have the standard or E1 bases, E2 bases, E3. And then we can produce two vectors, A and B. So A can be solely in the E1 direction. And I have this written as an example over here. A vector A solely in the E1 direction. A vector B solely in the E2 direction. I have this drawn here. And then we can do A cross B, do the math for it, and you get a vector that's equal to the magnitude of A, magnitude of B, times E3. So it's solely in the E3 direction. I have this also written in index notation for you. So you notice A cross B is given by the standard right-hand rule. When you go curve your fingers with the right hand from 1 to 2, you're going to get pointing up is going to be your A cross B. And the order of operations is reversed. In other words, if you did B cross A, the result points in the opposite direction. So here I have my summary of my right-handed system, my A, my B, my cross product. And now I want to consider a left-handed system. So in this case, again, remember we can only get a left-handed system if we do a reflection. So now our one basis vector, 1 prime, is going to go in the opposite direction as our previous 1 vector is. So our E1 is in this direction, E2 is the same, and E3 is the same. So this system can also be referred to as a reflection of the right-handed system about the x2, x3 plane. So this plane here, it's this one axis is reflected across this plane. And the equations relating the prime to unprimed coordinates are, well, x1 is now equal to negative x1, right? If we wanted to write that vector here, we're going to have to, since this E1 is in the opposite direction, we need a negative. x2 stays the same, and x3 stays the same. So now, using these equations, we can write the transformation matrix from the primed to the unprimed system. So x1 will be given a negative, x2 and x3 will stay the same. We can see that this is the correct transformation matrix by saying our x1 prime, x2 prime, x3 prime is equal to A times our x1, 2, 3. We plug in our transformation matrix for A, and you see we get negative x1, x2, x3. So I've kind of kept my summary here. So we're considering the left-handed system. It's a reflection. These are our formulas, and here's the transformation matrix. Now the next thing I can do is calculate A prime. So this is our original A up here in our right-handed system. So I'm going to write our A prime now is going to be our transformation matrix times our original A, which is A naught in the E1 position and then 0, 0. And we can see when we do the transformation, we're going to get negative A naught, 0, 0. Similarly, over here in our original right-hand system, we have B equals B naught E2. So we have, when we multiply by our transformation matrix, we're going to get 0, B naught, and 0. So B remains unchanged. Now if we do A cross B, so I'm going to put my A prime cross B prime. I'm going to have my A naught, 0, 0, and my 0, B naught, 0. And when I do the cross product, you see I get negative A naught, B naught times E3. So here are my graphs. This is my right-handed system bases, and then here I have an example A and example B. A cross B points upwards. Here I have my left-handed system where my E1 points in the opposite direction. In this case, I have my A is going to point in the opposite direction, B is here, so A cross B now is going to point downwards. Actually, I drew my A wrong. My A stays the same, but its coordinates is now in the negative direction. So here's my A prime, my B prime, and my A prime cross B prime. So what we have is, while the vectors A and B point in the same direction in the two systems, here's A and B, their cross product does not. Here the cross product points up, here the cross product points down. And you cannot just plug A cross B from the unprimed system into the transformation to find A cross B in the prime system. In other words, I can't say that A cross B prime is equal to, that's what we'd like to be able to say, but it's not equal to A times A cross B. So in other words, we can't just take this A cross B and then transform it, because when you take the transformation matrix on A cross B, which is A naught, B naught in the E3 direction, you get 0, 0, A naught, B naught, which is not the same thing as A prime cross B prime, which is what you would like. So this problem here, it presents us a problem. So what we say is this quantity formed by A cross B is a pseudo vector, because A cross B is not invariant under the reflection transformation. So we just saw A cross B, when you transform it with a reflection, you're not going to have something that's invariant. You're going to have something pointing in the opposite direction. So remember when we said reflections will bring about pseudovectors? Well, here we have a reflection, and we see that this cross product of two regular vectors will bring out a pseudovector. So the resulting A cross B, that we don't want to call A cross B a vector anymore. We're going to call it a pseudovector. And pseudovectors are also commonly called axial vectors, while regular vectors are called polar vectors. So if x is a regular vector, then it transforms according to our regular equations where we have our transformation matrix. And then for our pseudovectors, we need to add this determinant in here. I had to clear out room again. So here I have in my first right-hand system, my cross product. Here I have in my left or primed system, my cross product. And our matrix was over here, -1, 0, 0, 0, 1, 0, 0, 0, 1. So now if I take the determinant of my matrix, I see that's equal to -1. So when I do my matrix A with my A cross B, so I'm going to have my determinant first, because now my A cross B we said was a pseudovector, so we need to introduce the determinant. We need to introduce the matrix A, and then we put in our regular A cross B, which is 0, 0, and then A naught, B naught. And you see then we will get negative A naught, B naught as our third coordinate, which is exactly what A prime cross B prime is. So this is our correction factor if we're dealing with pseudovectors. The correction factor is exactly the determinant of your transformation matrix. To review what we've covered in this video, we started talking about pseudo objects and pseudovectors, and the significance of pseudo objects is when we started talking about tensors, we said that tensors were objects that were invariant under transformations, but up until then, everything we had seen had been invariant under transformations. So what we have are that we get these pseudovectors when we have reflections, or when we change from a left-handed system to a right-hand, or from a right-handed system to a left-handed system, or vice versa. We get things that are called pseudovectors, and these pseudovectors, in particular when we have reflections, are not invariant. And our first example was the cross product. So we considered two vectors and their cross product in a right-handed system. And this was our system where we had our first axis this way, our second axis, you rotate in a counterclockwise to get to it, and then the third axis is straight up. And we did our cross product, and we see this follows the right-handed rule. Now we're going to switch to a left-handed system. To do that, to get a left-handed system, we simply reflect this first axis across the 2, 3 axes. The 2 bases, 3 bases axes. So we reflect that across, and you'll see that now you get a left-handed system. And again, the system can be looked at as a reflection across the right-handed system across the x2, x3 plane. And the equations relating the prime to the unprimed system is x1 now, since it's in the opposite direction, one's going in the opposite direction, you're going to have to say that x1 prime will be the negative x1. And since x2 and x3, the bases are not changed, they remain the same. So you get this transformation matrix A here, which essentially just takes x1 and makes it negative. And then we calculated A prime. So we took our A prime from our right-handed system, we calculated its coordinate in the left-handed system, and no surprise, we see that now, because it's the same vector, but now it's pointing in the opposite direction as the positive direction of our primed system. So now A needs to be negative. Our B is the same because it's only in the second direction. And then when we do A cross B, what we get is negative A naught B naught E3. And so it's in the negative direction over here, which is exactly the opposite direction that we got in our right-handed system. And this was strange, or it was sort of a problem, because A and B point in the same direction in both systems, right? A points to the right, B points over upwards in the, northeast direction. Is that east? Yeah, that is east. Okay, here A points to the right, B is in the northeast direction. But the cross products point in different directions. So that means the cross product, when you have this transformation, this reflection transformation, is not invariant, right? You don't get the same vector. And so it's not just a matter of coordinates. They're pointing in different directions. So we don't call it a vector, this cross product of vector anymore. We call it a pseudovector because A cross B is not invariant under the reflection transformation. And then also to get around this problem, when I say to get around this, I mean this problem, this cross product not equaling the cross product in the other system. is that if we have regular vectors, we do our regular transformation matrix. However, if V is a pseudo vector, and then its components transform, we need to take in this extra factor here where we multiply our transformation matrix, or V times our transformation matrix needs to be multiplied by the determinant of A. And so that's it for our summary, and that's it for this video. Thank you for watching.